Well, I'm new to this field, and I'm hastily trying to understand what it is about. So probably I won't say anything original, just a compilation of some ideas. But I think I'm converging to some reasonable guess what the problem is. Of course, I'm nowhere near the solution, but just the problem. Let's consider a black hole, and it will be an old black hole or an eternal black hole. Let's draw it in Kruskal's coordinates. And there is a left interior and exterior, right exterior, and we live here in the right exterior. And to avoid problems with radiation escaping to infinity, we'll put a mirror. So there will be a mirror. Of course, there is a rigorous way to put a mirror using ADS CFT, but for me it's just some wall, so that to make the system finite. And on that mirror, we'll put additional degrees of freedom, qubits, which will interact with the radiation inside. This left thing is imaginary. We really live here. And in fact, we can only access the radiation on the surface, on the boundary. We can lower some object, but this should also be expressible in terms of the boundary theory. There are two different ways to describe what's happening here in this region, and they give different answers, and we need to reconcile them somehow. One way is the semi-classical one. We imagine that near the horizon, EPR pairs are formed, and those things fall down and eventually reach the singularity. But these things, some of them also fall down. Some of them bounce off the mirror, and as they're reflected by the mirror, they can interact with qubits that sit on the boundary. This is the picture. The essential part is that there is an unbounded, potentially infinite number of EPR pairs. If we wait long enough, this system will generate arbitrary large entanglement across the horizon. This is the semi-classical picture. And the semi-classical picture can be associated with a time slice or a family of time slices. And perhaps there is an associated Hilbert space. So we can pick a nice time slice that does this.
But the thing from here, I would have said not that it generates a larger and larger amount of entanglement, but that it comes to equilibrium that's finite.
It depends on how many qubits we have on the boundary.
I understand the role of the qubits on the boundary.
Right. We have full control of those qubits. So one way to use them is to swap each outgoing radiation quantum with a qubit. And this way we can generate arbitrary large entanglement. Now, the semi-classical picture holds for this time slice. And there is a different picture where we only have the right exterior with the qubits, but no interior. And we consider time slices like this. And in this picture, we hope to have a full quantum mechanical description with a finite Hilbert space describing the black hole. And of course, we can add arbitrary qubits. Now, I'll draw this time slice. There must be some relation between these two pictures. To make the question kind of simpler, let me just talk about a quantum mechanical system, not a black hole. And hopefully it's the same question. We can consider a situation where there is a chiral boson propagating along some edge of a two-dimensional material, and it comes back along the other edge. Here we put a qubit or a spin that interacts with that boson. And here we can put two different things. One possibility is to, to leave it open, infinite. And we can also use an electrical model. So we can make an infinite microwave line and make a loop, put a spin here, and this spin will interact with the magnetic field created by the current. And in this model, it's just a boson. It's a bunch of oscillators, basically. So we can write and we should put some coefficient in front. I guess it's this. R is the effective resistance of this line. And these bosons have this commutation relation. This is a semi-classical model. And there is a fully quantum model where we put some piece of metal, some complex object, hopefully rapidly mixing. Or we can just put a solid-state resistor. And this part is the same. Now, in this case, it's clear that these two systems are actually different. And if we consider correlations between currents I of t in the two models, they will give different answers. Now, during a short time period, those correlations will be very close. How long is this time interval? One can actually consider two different situations. One situation is where we just have this system at some temperature, and we don't have a purification of it, just the system. In this case, we won't be able to detect the difference for a long time. It may be as large as pages time, or maybe somewhat shorter, but it's a pretty long time. On the other hand, if this system comes with a purification, then those qubits will come out much faster. So in this case, in the case of a black hole, we believe that the mixing time is of the order of the Schwarzschild radius times the log of this. And in those systems, it depends on the details of these objects. So for long time periods, this model are different. And we want to come up with equation that can be formulated only using short time so that these two models can be matched. But still, it will be a highly quantum question. So, for example, the EMPS products can be.
I'm not sure I understand the second model. The second model is not just the same as the first model, except just looking at the Windler wedge?
Yeah.
It is?
It is the same model, yeah.
Oh, so why should there be why should there be a difference in
Well, right. Why there should be a difference? Our goal is to understand what happens in the interior. And the full quantum model possibly does not have the interior. It only has the exterior.
Let me ask you differently.
Yeah.
Are there boundary conditions on those on the light cones?
On these cones?
Yeah.
No. Here, well, there are no explicit boundary conditions. Quantum gravity should set some boundary conditions, but we don't know them.
So I'm trying to understand it. What way the second one is different than the first one?
So in this model, we can think of a straight horizon and imagine that the degrees of freedom live on the straight horizon. And they have some complex dynamics, which we will only know when we have the full theory of gravity. But hopefully the same thing can be formulated in terms of the boundary only. So this is the actual quantum gravity. Now, in the full quantum gravity, they may not be an interior region. And let me make a philosophical statement about this problem. We want to understand what happens in the interior. However, we don't really care what happens to an observer falling into the interior because he won't tell. We want to make some sense of the interior region in the full theory of quantum gravity, which we don't have yet. But hopefully it's a general feature, and maybe we can even make sense of the interior in those simple models. We want to make sense of the interior, particularly because we want to understand the early universe, the inflation, where there are lots of horizons. So if we can make some sense of the interior, then it works. So we can continue here. Now, later on, I'll show that the EMPS paradox can be formulated within this short time. But now I just want to give different views of this evolution, the full quantum model. One possible view is a quantum circuit. We have a straight horizon with degrees of freedom on it, and we have exterior qubits, and they interact. So it's basically a bunch of unitary gates on the straight horizon, and a bunch of gates for the external qubits. And there is some exchange between them. It's a diagram like this. It's a quantum circuit, but it's also a tensor network. It's a special tensor network because every node is unitary. So this is a perfectly consistent picture. Now, imagine that we do the following transformation of this circuit. We just take this set of qubits, which we fully control, and these are the gates acting on the external qubits. And there are some inputs and outputs. It's the exchange with the stretch horizon. And instead of taking the actual input, we'll act by this gate on an EPR pair. Just this. So this is a rather silly circuit because it just creates lots of qubits. Now, if we take this circuit and the output state, and then later stick in the other part of the circuit, do the tensor contraction, it will work. It will give the right answer. So that's roughly how post-selection quantum mechanics works. I say post-selection because this circuit can be conveniently put on the singularity. So now we have some tensor network on the singularity, and some qubits on the boundary, and they exchange in a complicated way. But this way of drawing will involve going backward in time. So we can imagine that there are two EPR pairs. Okay, maybe I'll draw it this way. This is one EPR pair. This is another one. And there is a final projection. There is a potential problem because if we take this cross section, then there are two copies of the same qubit. This copy is in the past, that copy is in the future or now, and potentially they can conflict. We can try to send a signal along this time-like curve, closed curve. The first thing we should make sure that we cannot send a signal to the past. And this seems to require some fine-tuning, because in general we can. Now, I think the solution is that this circuit, tensor network, does not really live on the singularity. It lives on another stretch horizon that is it can be drawn like this. in the interior region. And that does not require any fine-tuning. Then we push it to the singularity using the unitary evolution, and it appears to be fine-tuned. Let me say a few more words about that. So imagine that we have exactly that picture with, maybe I'll erase everything and just leave the picture of the information flow. So the picture is this. And we're sending C into the black hole, and we're trying to swap these two qubits. We're trying to swap A and C. And if we can swap them, then we will create a loop. And that is bad. So can we actually do that? Can we send a signal to the past? Maybe we can, but it's easily avoided, especially if we have some amount of tuning. Because when we send a signal, when we send this qubit C, we increase the energy of the black hole, and the Hilbert space grows. And there is some room to tune the thing so that no signaling happens. However, we may ask a different question. Suppose we send a probe. I prefer to talk about an inanimate object. We send a probe which is going to test quantum mechanics, or to test whether the interior looks like we think. And that probe goes to this point and decides whether the experiment is successful or not. We won't know, but in some sense the answer exists.
The experiment is successful means what?
Successful means that the interior looks exactly like we expect.
Which means?
No firewall, nothing special. Well, it's an artificial question, and it has an artificial answer, but it does have an answer. So we can define some rules of probability for post-selected quantum mechanics. This won't be a probability, because usually when we have a projector P or an operator X, then the probability W of P is equal to trace P times rho. In the post-selected quantum mechanics, it will be more complicated. We take the trace of, let me write from the right. First we apply the projection, then we apply the final state operator, then F dagger, another projection, and this is W of P. And this thing can be larger than 1. And moreover, if we have a partition of unity like P0 plus P1 equals identity, then the probability won't add up to 1. The probability defined in this way. So these are not really probabilities. They do not obey the laws of probability. But in any case, we can calculate the quantity, and maybe it's useful for something else. So I want to calculate that quantity. And I want to use the post-selection picture. I'll do it in a different way. And I believe it's equivalent, and the philosophy here is very similar to the paper of Maldacen and Saskian about cool horizon kind of entangled state between two black holes. So the philosophy is this. If we have a black hole, we may not get an answer for it in the general case, but only when the qubits on the horizon form a purification of the usual black hole state, and furthermore, we can identify those qubits with the interior, with the left exterior. And of course, that would be boring, but we can consider slight variations of this setting. So the Hilbert space here, H, is L sub L tensor L sub R. This the individual. Let me write it the other way. The individual Hilbert spaces for the right wedge and for the left wedge, and the left wedge will be equal to L sub R dual, and the Hamiltonian is HR minus H R star, and of course HR star is the same as HR transposed. So this is the Hamiltonian acting on the qubits. So we assume that our system is in the unroot state of this Hamiltonian or close to it. And for that system, we can do the calculation. So this is a possible experiment. First, we modify this state. We start with this state psi now, this is the right wedge, this is the left wedge. It's a bit awkward, but it's okay. Now, this J can be turned into a ket vector, and then we may write that psi is the square root of rho, the density matrix. Now, we first modify this state psi by acting by some operator. We take psi and entangle the right exterior and our qubits by some operator U. And then we use this density matrix, or we use this state to do an experiment, which is this. We send a probe. Sending a probe means acting on the boundary, and the action is on both the qubits and the gravitational degrees of freedom. And in fact, sending the probe can be described by this U. So this is actually the operation of sending the probe. And there is another operation. In this region, there is an observable O, which represents the decision of that probe, whether it looks like, whether the interior looks like the usual vacuum from this side or not. So we can do this calculation.
When you write O, could O just, for example, be the energy momentum tensor, or just some ordinary thing, and you test it to see whether it has a more or less vacuum?
Yeah, well, it can be a projection. It can be something that involves interaction with extra stuff sent to the black hole and the local energy momentum tensor, something like that. So this O can be written as in a tensor decomposition. And this X acts on the right exterior. Y acts on the left exterior, which is equal to LR star. And let me write it YK transpose.
You need a dictionary, right, between the X's and Y's which live in the, which act on your qubits, right? They act in your systems of qubits on the outside, and the local question you want to ask inside.
Right, but I'm trying to build the dictionary by way of example. I just want to solve this problem, and we'll see what's going on. In this case, we're using the semi-classical picture.
The operator contains both some, let's say, the energy momentum tensor or something, and also the probe?
Yeah, also the probe, right. So it contains modes coming from here, including the probe, and modes coming from this side, which is supposed to be vacuum. So now, how do we use this operator? The first thing is to formulate it not using the left exterior, only the right exterior. So if we start with psi and apply O, this is equivalent in that notation, where psi is the square root of rho. It's equivalent to this. It's sum over k xk rho to the 1/2 yk. And it's a new state, but we want to say that the same state can be obtained by acting in the physical region only. And to do that, we write it in this way. We write it rho to the -1/2. This will be an operator acting on the physical region times rho to the 1/2. Now, this rho to the 1/2 is actually altered. It's altered by the operator u. So let me write eta instead. And eta or we may say this u is equal to sum over m zm tensor wm transpose. And if we write it in the operator form, not as a ket vector, it will be sum over m Zm right. Okay, I made one mistake, but I'll fix it. Zm rho Wm transpose. Now, if we do that, we actually get some mess. It's rho to 1/2. Because we have Z in here and W on the right. So there is a Z between rho to the -1/2 and that rho to the 1/2. But actually, it's not there. And that's because Z acts on the physical degrees of freedom. So U is an operator acting here, and it consists of Z acting on the physical degrees of freedom and W acting on the qubits. That's what it does. And if we think about the Z acting on the physical degrees of freedom, it acts after this entangled state has been formed. So we should actually move Z to the left. And it should be applied before xk. So the answer is it's sum over k and m, xk, zk, and instead of eta, we take rho 1/2 Wm digger, and these two cancel. And now I should say this is without transpose. Now we can reinterpret it in terms of KIT vectors and draw a diagram of a circuit. But it won't be a regular quantum circuit because it begins with this state psi. So then we have zk, and on the right we have yk, and then we have xk. I should use k and m. M is used for z, I think. Z, yeah, zm. Wm. And here it's transposed. And it's xk. And so this looks like a cross application of two unitary gates. This is one unitary gate, and that is another unitary gate. And since they are applied in such an unusual way, the result is not unitary, but it's a well-defined result.
Could you say again where Z and W came from? So X and Y are your observable.
X and Y are observables, and Zm, tensor Wm, is the operator that sends the probe. Zm acts on the physical degrees of freedom. So, no. Oh, yeah, right. W acts on the left space. Yeah, that's true. Yeah. W are the physical qubits that live here physically, But we may think of them as representing the left region. But physically, they're here.
What's the intuition for that? That the qubits can be represented on the left? How do you think about that?
Well, I think I just used some formal manipulation. So I haven't actually used that.
But
I
there's one hole. I think those are the boundary connections. But Z and W are both could be identified with the probe, with creating the probe?
Z acts on the gravitational degrees of freedom. W acts on the qubits, but they together form a probe.
Together they form a probe. Okay.
Isn't it find the qubits from the left side?
Yeah, the qubits may be identified with the left side.
So if we're, instead of writing one HR minus HL, we write HL as HR star. That's the identification.
Yeah, yeah. Yeah, exactly.
It's all, I think, the
Oh, it is.
Yeah. Yeah, so the conclusion is that we can do calculations in the postulated quantum mechanics, and hopefully we can build the right model from some usual quantum mechanics problems. Yeah, that's it. Yeah, yeah.
Oh, sorry.
No.
I just had a naive question. I know very little about quantum circuits, but I always sort of picture them going from left to right with some sort of time ordering. And now you seem to be having much more, not just this one, but even earlier, that some much more general topologies for quantum circuits. Is that still a sensible notion? Or do they always have kind of an ordering like that?
Unitary quantum circuits have an ordering like that.
Mm-hmm.
This is not a unitary circuit. And if we start with a vector of norm 1, the result may have norm greater than 1.
Do these have other applications?
I don't know. Oh, no, it's a pure state of norm greater than 1. We can calculate its norm, and that would be the post-selected probability, which may be greater than 1, whatever that means.
Okay, well, we have a discussion scheduled for 2 o'clock. So if there are no more questions, we'll see you. It didn't get there up to 2 minutes.